Alright, so now we are going to try our cost functions. Okay, before that I just plotted those three kind of activation functions in a single graph just to kind of club them together. So I just have wrote down the functions, and let me quickly go through it so that you can also understand. This is the definition for the mean square error, okay, quadratic cost functions, where we are taking the element wise difference between the true class y and the predicted class a, and we are taking the square of it, and then we are taking the average of sum of squared error. Okay, and in this particular case what we are doing, we have applied that cross entropy cost functions. We are taking the sum of y into log of predicted values plus the multiplications of 1 minus actual values into the log of 1 minus predicted values. Here length y is basically number of items we are considering together to calculate the cost function. Okay, so believe me, this is the equation whatever I wrote down in the previous presentations. Okay, you can try it by yourself. So what we're going to do now, let me compile this particular line. Now we will try a few of the things. Okay, first of all, let's assume that y equal to two examples we have, and both of them are 1. Okay, now our predicted value, this is y hat equal to, I would say 0.1 and 0.1. Okay, so we have predicted something very close to 0, okay, but far away from 1. Let's see how our mean square error gives the cost values for mean square error. Okay, so what are we going to do? Y and y hat. So, okay, let's see. All right, it is giving 0.81. Okay, now we'll try the same example, like 0.9 and 0.9. Same error. You can see it has reduced dramatically. Okay, and not necessarily you have, like, this one was predicted correctly, but the second one was predicted very close to the original values, but not exactly the same. Okay. In that case, the value has reduced once again. Okay, if it is exactly the same values, it is the cost amount is 0. Okay, the same predictions. Let me try to for cross entropy as well. Okay, this is what y hat. Let's see how it gives. Okay, not a number. All right, so ignore this particular element actually. So only for demonstration purpose, we have same consideration, like the predicted value is 0.1 while the actual values are 1. Okay, so cross entropy is giving some good higher values like 2.3. Now the more we'll increase the predicted values, we should see a drastic drop of the cross entropy values. Okay, 2.5 to it has reduced to 0.5, and if you reach like 0.9 and 0.95 somewhere, it's very close to the original values, then the cross entropy will also come to the similar to the kind of very close to zeros. Alright, this is how we are calculating the cost amount for basically the error values between the original class and the predicted class. Okay, another thing I promised to discuss, that was the SoftMax layer. Okay, softmax function. Alright, so let me try to create similar function. Softmax. Alright, so let me define the function. Define softmax of x, and what it will return? It will return a numpy dot exponential of x divided by sum of numpy exponential of x. All right, exponential of x. I think we have done it properly, and to kind of, for your simplicity, let me round this content. Okay, then it would be easier to understand. I hope I am doing it right. So far no issues. Now assume we have these net input values which contains 1, 2, 0.5 and 0.8. These are the 4 values we got. Visually we can see that the second element contains the highest values. Okay, if we make the categorical probability distributions, this second content should have the highest probability from softmax. Okay, let's try it. Let's see whether our function is saying the same thing as we are expecting. Alright, oh yes, our second element is saying that there is a probability of this particular prediction, this particular example to belong to class 2 is 0.5, while the other classes have the probability of 0.2, 0.1 and 0.1, 0.5, 1.6, somewhere close to that. So this is how we convert the numbers to a probability distributions among those multiple classes. If you take a sum of all these numbers, I'm sure you will come to very close to 1 or exactly 1. Alright, so this is what softmax all about, and you will be using this particular function many times during our practical implementations of deep learning models. Alright, so alright, that's all from the kind of first practical session. Okay,